How are you all doing this morning?
Doing good. How are you?
I'm doing well. Today we are going to talk about complex power relationships in three-phase circuits. And this should largely just be a review of what we did for single-phase circuits with one subtle change. So and actually, let me specify explicitly that it's balanced three-phase system. All right, so let's say that we have a YY circuit. This is our voltage VAN, here's VBN, here's VCN. Transmission line. And here is our load. C, and capital. All righty, so through the A phase of the load, we know that we should have some phase current, IAN. Through the B phase, we should have some phase current, IBN. And through the C phase, we'll have a phase current, ICN. And we will also have some phase voltages, VAN, VBN, and VCN, like so. So the complex power absorbed by the A phase of the load is going to be S, let's call it A, is the voltage drop over the load as an RMS phasor, so VAN, multiplied by the RMS current, IAN, conjugate. Nothing crazy wild there. And I'm going to rewrite this as the magnitude of VAN times the magnitude of IAN with an angle of theta VAN minus theta IAN, right? When I multiply those two numbers polar complex numbers together. It's just the product of their magnitude with an angle of the, it's going to be a difference here. And the reason that it's a difference is the conjugate operation, right? So it's going to be negative, so theta BAN plus negative theta IAN. And we can further simplify this just a smidge by saying that this is magnitude of BAN times the magnitude of IAN times the angle theta ZY. Because by definition, the voltage, the angle of the voltage minus the angle of the current is the same as the angle of the impedance. Okay, so for the B and C phases, we will have SB is equal to VBN multiplied by IBN conjugate, which is going to look like the magnitude of VBN times the magnitude of IBN, angle theta ZY. I'm just skipping that intermediate step. And similarly, complex power absorbed by the C phase is going to be VCN ICN conjugate, which is VCN ICN angle theta ZY. And we know that the magnitude of VAN, VBN, and VCN are equal for a balanced three-phase system. We know that the magnitude IAN, IBN, and ICN are identical for a balanced three-phase system. So from these relationships, we can find that the total complex power absorbed by the load is we'll call this S three-phase. Oh, and I'm sorry. These S's shouldn't have a squiggle because they're not an RMS quantity. They're just a complex number. That's my fault. It's just semantics at this point. But, it's simply going to be 3 multiplied by what I'm going to call VP, which is the magnitude of the phase voltage, times IP, which is the magnitude of the phase current, angle theta Z, the angle of the impedance. So I'm just going to specifically put here that this is VAN, this is magnitude of IAN, so yeah, so if we can find the power, complex power over any single phase, then we just multiply it by 3, and that's our power for all 3 phases. Should make perfect sense, because if they all have the same magnitudes of voltage and current, they should all be absorbing the exact same amount of power. Now, we can also get an alternative definition here, okay? So we can recognize that our line current, IAA, line current, IBB, and line current, ICC are the exact same currents as our phase currents through our load. We can also observe, let's do this color, that there's a relationship between our phase voltages and our line voltages. And you know where VBC is. So we can find that S3 phase is simply equal to the square root of 3 VL IL theta Z, where VL is the magnitude of our line voltage VAB or VBC or VCA, and IL is the magnitude of our line current IAA. And this is all because we know that VL is the square root of 3 VP. And IL is equal to IP in a YY system. So we've derived these relationships for a YY system. Really, we've derived these relationships for a Y connected load. It didn't matter what our source looked like in this case. But we could find actually pretty easily that in a delta system, we would get the exact same results. And the reason is that in the delta system, we know that the phase voltage and the line voltages are the same thing. But in a delta connected load, we would find that the line currents and the phase currents are the ones that have a square root of 3 angle 30 degree relationship. And we've already actually seen that in a couple of the example problems that I have worked, where when we were trying to find line voltages, oops, what the heck did I just do? No, I don't know what that is. I just know I want it to stop. All right. So these equations work for any three-phase system. I've only derived it for the Y-connected, and I'll leave you guys to take me at my word that the delta-connected works the same way. All right, so our average power relationship then. The total average power, which we'll call P three-phase, is by definition the real part of our complex power so this is going to give us simply 3 Vp Ip cosine theta Z. Or if we want to use our line quantity equations, our reactive power is the imaginary part, so let's call this Q three-phase. Which would be 3 VPIP sine theta z. And let's come out over here. Our apparent power is simply the magnitude of S. Three-phase is the magnitude of S of 3 VPIP angle theta z, which is just 3 VPIP. L IL, excuse me. And lastly, a power factor of our three-phase system will be, by definition, the ratio of the average power divided by the apparent power, which will be just cosine theta z. And that's true whether we're dealing with line quantities or phase quantities. So really the only change in calculating complex power that we have to worry about from the only change from single phase to three phase is multiplying by 3, because there's 3 times as many loads. So fairly straightforward there. All right, any questions on any of these relationships before we jump into an example problem? All right. So for our example problem, let's consider a YY circuit. Excuse me just a moment. I need to go tell my dog to be quiet. All right, so A, B, B, C, little n, big N. So we're looking at this guy in the time domain for right now, and obviously we'll need to switch it to the frequency domain at our earliest convenience. So if we know that VAN T is equal to 100 root 2 cosine 120 pi t volts, which would be a common voltage in the northern part of Japan, I believe. I want us to find these three quantities.
Quantity is a property that
I did not talk to my stupid phone. I didn't say, hey Siri once. The total reactive power absorbed by the load the total average power absorbed by the transmission lines and finally power factor at which the source supplies power. All right, so hopefully it's pretty obvious that we're going to wind up working this thing in the frequency domain. So we can convert our time domain voltage to the frequency domain, specifically the RMS phasor domain, as what? You guys remember how to convert time domain signals to phasors?
100 square root of 2 angle 0.
Okay, so that would be a phasor. Now how do we convert to the RMS phasor?
Oh, over square root of 2.
Yeah, so 100 angle 0 volts RMS. Alrighty. The impedance of our transmission line, which I'm just going to call ZW, is going to be 10 ohms plus J omega, which is 120 pi radians per second, times L, which is 5 millihenries, is going to give me 10 plus J 1.88. And the impedance of our load, which I'm just going to call ZY, is going to be 40 plus J 120 pi radians per second times 40 millihenries is going to be 40 plus J 15.08. So from this, we have enough information to draw our single phase equivalent circuit, right? Capital A, and little n. So this is 100 angle 0 degrees volts RMS. This is 10 plus J 1.88 ohms. And this is 40 plus J 15.08 ohms. So we want the total reactive power absorbed by the load. So what do you think the easiest way to get the quantities we need is? So R, whatever the correct conjugated form of the verb can be. Yeah.
First we need to find our current.
Okay. So we can find our phase current, which will be the same, exact same thing as our line current. So that's going to be this current IAA, which is the same as IAN. All right, I got no problems whatsoever with that. So let's call it IAA, which is equal IAN, is going to be the voltage divided by the total series resistance. So that's going to be 10 plus J 1.88 ohms plus 40 plus J 15.08 ohms. And up here we have 100 angle 0 degrees volts RMS. And I get this to be 1.894 with an angle of negative 18.742 degrees. Amps RMS. So now that we know that current, that's actually practically the only thing we need to know to get at least A and B solved. So let me explain why I say that. Okay, so let's look at A, where we're trying to find the complex power absorbed by the load. Or we're going to use the complex power absorbed by the load to find the reactive power, because that's my preferred methodology, is to find the complex power for everything and then use that to get the other pieces of information. So we know that S three-phase, and I'm going to put a Y here because we're looking at the Y load, by definition would be 3 times the voltage VAN that we don't know, multiplied by the complex conjugate of the current IAN, which we do know. But VAN could be written as IAN times ZY. And I don't want to put an absolute value there. This should be a bracket. Times IAN. Everybody okay with what I just did there? It's just Ohm's law.
Yes.
All right, so this is the same as me having 3 times IAN conjugate times IAN times ZY. Well, what's IAN times IAN conjugate?
Is it just one?
No. So I'll do it down here and I'll erase it. Let's say that I have a complex number A is equal to A e to the j theta. A conjugate times A is then going to be A e to the minus j theta times A e to the positive j theta is just going to look like A squared. So whenever I multiply a number by its complex conjugate, I just get the magnitude of that number squared. Seem legit?
Yes.
All right. So magnitude of IAN squared times ZY. So that's going to be 3 times 1.894 amps RMS squared times ZY is 40 plus J 15.08 ohms. And from this I get 460. Sure. Let me give it to you in rectangular. 430.447 plus J 162.275 VA. So since I have my complex power in my rectangular form, what is the reactive power?
Your imaginary portion.
Right, so this guy right here is Q 3-phase Y. So for part B, when I want the average power absorbed by the transmission line, I can say pretty easily now that S 3-phase wire is just going to be 3 times the magnitude of IAA quantity squared times the impedance of the wire. I hope I don't have to do that derivation again. And so from this, that's 3 times that same current, 1.894 amps RMS squared times the impedance of my wire, which was 10 plus J something, 1.88. And I get that to be in rectangular form, 107.612 plus J 20.284. And my average power is then what?
107.612.
Right, just the real part, nothing crazy there. So P, that's not a P, that's a B. 3-phase. All right. So for part C, the only thing that we've determined in this whole thing thus far, really, is the current. Let's see. So we know the current flowing through everything, and we know the voltage drop over it. So that should be enough, right? So yeah, we know the voltage and we know the current, and the current is flowing into the negative polarity terminal, which is good enough for us. So S, and I'm going to do one phase, right? Because we only have the information provided in our A phase equivalent circuit for the source. So that's what that S is going to be, is the voltage drop over the source as an RMS phasor multiplied by the current flowing through the source, which we know to be our line current IAA conjugate. So our voltage drop over our source as an RMS phasor is 100 angle 0 degrees volts RMS. Our current is 1.894 angle. So I'm taking the conjugate, so it's going to be positive 18.742 degrees amps RMS. And this should give me 568. Maxwell, please stop. 0.186. Angle 18.742 degrees volt amperes. And so our power factor at which our source is supplying power is the cosine of 18.742 degrees, which is 0.947. And is this power factor going to be leading or lagging?
Lagging
You're correct, but do you know why you're correct?
because the angle is positive.
You are absolutely right. Great. All right, so we're done there. Now, we could have gotten the power factor in a slightly different way. So as an alternative solution, this one isn't any harder or easier, really. The total impedance is 10 plus J 1.88 ohms plus 40 plus J 15.08 ohms. Let me find my calculator real quick so I can add those two numbers together. $52.798 angle 18.74. And we could take the cosine, of that angle, and we would also get the power factor. So try not to forget that the power factor angle is simply the angle of the impedance as well. That's a way where in a lot of questions you're asked the power factor about a particular load or something like that. You don't ever need to figure out the voltage or current. If you know the angle of the load, or if you know the impedance of the load, then you know the angle, which means you know the power factor, never knowing what the voltage or current or anything like that is. So it's just a quick way to get the results you're looking for. Okay, so we got 35-ish minutes left. So we can either cut out now. Do you guys have any questions about any of the homework or anything like that? Do you want to look at the homework problem regarding three-phase power? I don't know, whatever you want to do.
I wouldn't be against looking at a three-phase power homework problem.
Alrighty. Let's see, 223. Summer. Homework. Slightly smaller. All right, so problem one, I don't give you a circuit diagram or anything like that. And that's one of the great things about a lot of the power problems is it really doesn't matter whether or not you're looking at a YY system, Y delta system, etc. So what I mean by that, if we take a look at problem one here, it says that we have a balanced three-phase source, doesn't tell us whether it's Y or delta, is used to power the following loads. And then we're told the apparent power at which the loads operate and their power factor, which is enough information for us to determine the complex power absorbed by each of the two loads. We are given the line voltage at the loads, and from that we want to determine the magnitude of the line currents and the power factor at which the source is supplying power. So let's take a look at problem one real quick. And this is actually probably enough space. So we know that load one operates at 60 kVA with a power factor of 0.8 lagging. And load two operates at 30 kVA at a power factor of 0.75 lagging. We are told that the line voltage at the load, so VL is 208. And what else are we told? Our frequency is 60 hertz. Don't think we'll need that one, but we'll write it down anyway. We need magnitude of the line currents, the power factor at which the source is supplying power. All right. So how might we go about determining the total complex power absorbed by load one?
Use the definitions of power factor to get both the magnitude and the angle.
Sure. So we have, we're told that it's absorbing 60 kVA. So what does the units of kVA, like what quantity is that? Is that apparent power, average power, or reactive power?
That apparent power.
Right. By definition, the apparent power is the magnitude of our complex power, so we don't need to divide by the power factor or anything here. So we're going to have 60 kVA, and our angle is going to be the inverse cosine of our power factor angle versus our power factor, which is 0.8. So that's going to be 60 angle, let's see, inverse cosine 0.8, 36, excuse me, 0.87 degrees kVA. Complex power absorbed by load 2, 30 kVA, angle inverse cosine of 0.75. 30 angle 41.4041. All right, so where can we go from here? We are 2 steps away from answering both questions.
Just use the definition of your apparent power to find IL.
I don't quite follow your line.
Wait, hold on.
So in our system, let me draw a little makeshift picture real quick that I'll probably wind up deleting in a second. We have 3-phase source, and they're going to be 3 line currents, and then we have this total 3-phase load is presumably those 2 loads connected in parallel. We have, well, no other way that they could possibly be connected. So we're trying to find the current that's flowing from the source to the load in the transmission line, all right?
Yeah.
We don't care about how much branches off and flows into each of the individual loads. So, do we have enough information to figure out what the total 3-phase load is, at least from a power standpoint?
Oh, yeah, you just multiply by 3.
All right.
Wait.
You're not quite catching what I'm throwing.
Okay.
Okay. So let's talk about this. All right. So this S load 1 as the total power absorbed by load 1. Okay. So it's not
Yes.
by a per phase basis, it's for all 3 phases, because we were not told specifically that it is it's that amount per phase. So we have to make the assumption that that's the total absorbed by load 1. And we also have the total amount absorbed by load 2. So I would argue that S load is simply S load 1 plus S load 2.
Oh.
Right? The total amount of complex power absorbed by the loads is just the sum of the complex powers absorbed by the loads. Seems reasonable enough.
Yes.
Right? Okay,
Yes.
so let's add those 2 things together. So we're going to have 60 angle inverse cosine of 0.8. I'm trying to get a fairly exact one, and I didn't bother to store the numbers. 30 angle inverse cosine of 0.75. So I get 89.937 with an angle of positive 38.383 degrees. Kilovolt amperes. Okay. So I said that we were 2 steps away from answering both of those questions. So now we are 1 step away from answering the IL question and 1 step away from answering the power factor question. So let's start with the power factor question, because that's the one that's probably a little bit easier. So would you agree that the power factor at which the source supplies power is the same as the power factor at which the load absorbs power?
Yes.
Right, okay. So from that, to answer part B of this guy, PFS is going to be what?
The cosine of the angle.
right? So cosine of 38.383 degrees. Store that into here. All right. So cosine of polar angle 0.784. And it's flagging because the angle is positive, which I'm not going to grill you on it again because you've already proven to me that you know it. All right. So power factor, pretty straightforward there. And the beautiful thing about determining the power factor is it doesn't matter if you have three-phase powers or one-phase powers because it's a ratio. So it's the same either way. Okay. Now we want our line current. Now, I don't expect you to recall this equation right off the top of your head because we just learned it a few minutes ago. But we know that S three-phase is root 3 VL IL angle theta Z. So that means that the apparent power, which we know, we also know the angle too, but that's just going to complicate the math, is simply square root of 3 times VL times IL. Well, we know VL because it was given to us, and we know S3 phase. So I can say the magnitude of my line current, IL, is simply S3 phase divided by root 3 VL. Just using good old algebra, right?
Yeah.
Okay. So that's going to be 89.937 kVA divided by root 3 of 208 volts RMS. Is that, yeah. So I get 249.641 amps RMS. One three seven times 1,000 divided by 3 times.
That's the same thing I got.
Okay, cool deal. So that's homework problem 1 finished. Pretty simple and straightforward, I feel. So let's look at problem 2 real quick. Don't know if I'm going to work it or anything, but we can talk about what's going on here, right? So a similar situation, except that there's several more loads, and you're not given the apparent power for all of them. You're given the average power for loads 3 and 4, right? So that means you're going to have to change the relationship that we use slightly. But as you stated earlier, Sadie, it's exactly just using the definition of power factor to figure out what to do there. We have the line voltage at the loads is 600 volts RMS at a frequency of 50 hertz. So apparently this system is operating somewhere in Europe. And we're given a line impedance of 0.02 plus J 0.04 ohms. We want the magnitude of the line voltages at the source and the power factor at which the source is supplying power. So it's going to be a very, very similar process. We would find S load 1, S load 2, S load 3, S load 4, and add all these together to get S load total. We can use that information to get the magnitude of our line currents, which we're not specifically asked for. However, if we know the magnitude of our line currents, then we can determine S wire, which is going to be necessary. So our transmission lines have some characteristic impedance, which means there's going to be complex power absorbed by our transmission lines. Well, if we add these two quantities together, that gives us enough information to determine the magnitude of the line voltages, because we know the magnitude of the line current and we know the total complex power. And if we know all of the total complex power, we can determine the power factor. So it's a very similar problem in style, just a couple of extra steps because we have that line impedance to worry about. So nothing wild or crazy there. Problem 3 here. We are given the specifics for a balanced three-phase system where load 1 absorbs some power, load 2 absorbs some power, and we don't know what's going on with load 3. We're given the line voltages of the loads, we're given the total apparent power absorbed by the composite load, and we are given the power factor at which the source is supplying power. So we have load 1, load 2, load 3 is unknown, and we have enough information to say that S load 1 plus S load 2 plus S load 3 is equal to some specific value, which should allow us to determine what's happening in load 3. And then we're asked to kind of fill in the blanks here. So we want the average power, which is just the real part of S load 3, and the power factor at which load 3 absorbs power. So fairly straightforward. We're just changing the order of the steps a little bit, or changing the order in which we know information. Problem 4 is power factor correction, and problem 5 is power factor correction, and that's going to come on tomorrow. So we will get to that shortly. Alrighty, so yeah, there we go. Seems in my mind fairly straightforward. I don't think I've made anything too wildly insanely tricky for you guys. Any other questions about this or any of the previous homeworks on three-phase power or anything? Or three-phase systems, excuse me.
No, I'm good. Yeah.
Alrighty. All right, well, thank you guys for waking up bright and early this Monday morning. I will catch you tomorrow.
Bye.